Hello guys, and welcome to another calculus video. In this video we're going to be tackling this awesome infinite sum, which many of you probably already know is equal to pi cubed over 32. It's a relatively common sum that'll pop up in different situations. Traditionally the way it's solved is using Fourier analysis, but if there's one thing you guys should know about me before watching my channel, it's that I hate Fourier analysis. Don't ask me why. I don't have a good reason. I just don't like it in general. So I try to find as many ways around Fourier analysis that I can whenever I'm doing any type of problem. So I've come up with 3 separate solutions that we can use in order to figure out the solution to this problem. So let's go ahead and jump right into it. So the first method we're going to use is actually based on the video that I did very recently on what I like to call the digamma bar function. It's sort of a function that I came up with, but it's just equal to the sum from n equals 0 to infinity of -1 to the n over n plus x. And I'm sure you guys already see the comparison to the sum that we're about to evaluate. And one curious identity about this function is that digamma bar of x plus digamma bar of -x, or of 1 minus x, sorry. 1 minus x is equal to pi cosecant of pi x. And what we're going to go ahead and do is just differentiate both the function twice and this twice. So when we differentiate twice, we're just going to get digamma 2 bar plus digamma 2 1 minus x. Because of chain rule, we're going to multiply by -1 twice, but those are going to end up canceling. And on this side, differentiating once would just give us pi squared cosecant cot of pi x negative. So differentiating twice is going to give us pi cubed cosecant pi x cot squared of pi x plus pi cubed cosecant cubed of pi x. Next, we're going to plug in 1/2 right here. We're going to get 2 times digamma bar of 1/2, since 1 minus 1/2 is also just 1/2. And this whole term is going to disappear because cot of pi over 2 is just 0. Cosecant of pi over 2 is just 1, so we're just going to end up with pi cubed. So that tells us that digamma bar of 1/2 is equal to pi cubed over 2. Now, how does this relate to our problem? If we go ahead and take the second derivative, or sorry, digamma, this should have a 2 here. Take the second derivative of the digamma bar function, which is pretty easy. I'm just going to go ahead and skip to that step. We're going to get the sum from n equals 0 to infinity of -1 to the n times 2 over n plus x cubed. And if we plug in 1/2 right here, we're going to see some pretty cool similarities to our summation. If we go ahead and multiply by 8 on the top and bottom here, we're going to get this result right here. And then if we go ahead and substitute in this right here, we're going to see that pi cubed over 2 equals 16 times this sum without the 16, which I'm just going to call s in this situation, which tells us that s, which is what we're solving for, is pi cubed over 32. So that's just one of the many uses for this function that I played with on one of my recent videos. I'm gonna be honest, I was not expecting to find such a nice use for this function so quickly, but it just happened to work out in this manner. So yeah, I think that's a pretty cool method. Alright, so the next method we're going to use involves a pretty interesting identity. So we're going to take a look now directly at the sum. And something that I want you guys to always think about when you see some linear expression of n in the bottom is how can I write this as an integral? So the first thing is, let's say for example that we didn't have this cubed here. What I tell you guys to do is think that the integral from 0 to 1 of t to the a dt equals 1 over a plus 1. And then we could rewrite it, replace a with 2n, and then rewrite this as an integral and solve it incredibly easily. But we do have that cubed there. So how can we turn the right side of this equation right here into 1 over a plus 1 cubed? I'll let you guys think about that for one moment. And if you guys thought about it, the answer is we're going to differentiate both sides with respect to a. So when we do this once, we're going to get that the integral from 0 to 1 of t to the a ln t dt equals negative 1 over a plus 1 squared. And if we differentiate again, we're going to get that the integral from 0 to 1 of t to the a ln squared t dt is equal to 2 over a plus 1 cubed. So if we go ahead and substitute this in, we're going to get the sum from n equals 0 to infinity of the integral, or I guess I can put this negative 1 to the n out here, negative 1 to the n, of the integral from 0 to 1 of t to the 2n ln squared t dt. All right. Next, we're just going to go ahead and exchange the order of integration and summation and rearrange everything inside. We're going to get the integral from 0 to 1 of ln squared t times the sum from n equals 0 to infinity of negative 1 to the n. Actually, we're going to have negative 1 to the n, t to the 2n, which is the same as negative t squared to the n. T. Rewrite this using the geometric series, and we have the integral from 0 to 1 of ln squared of t over 1 plus t squared dt. All right. Now this integral is a little bit tough to solve. The first thing that I would think of doing to solve this integral is just do the exact opposite of what we just did and turn it back into that summation. But there is another easier way to solve it. So I'm just going to go ahead and call this I, and it's also equal to s, I guess. So I'm going to get rid of this. One tricky substitution you can make whenever you see something with a power of t plus 1 on the bottom and ln, something with ln on the top, is the substitution t equals 1 over u, or u equals 1 over t, whichever you want. When we make the substitution, dt is going to be negative 1 over u squared du. And instead of going from 0 to 1, we're going to be going from infinity to 1. Then on the top, ln squared of 1 over u is the same as ln squared of u, because ln of 1 over u is negative ln u. Then we're going to have 1 plus 1 over u squared times negative 1 over u squared du. And then when we have this negative sign absorbed into this, we can just flip our bounds right here, and we're going to have ln squared of u over 1 plus u squared du. And see that this is actually just the same thing as our integral of ln t. We're just integrating over different bounds. So if we add together our two integrals here, we can change this name to t, since this is just a dummy variable. And then when we add them together, we're going to get that 2i is equal to the integral from 0 to infinity of ln squared of t over 1 plus t squared dt. All right, now it's time to introduce the big guns. So now, whenever we see the integral from 0 to infinity of some power of natural log over a polynomial on the bottom, or I guess a power of x plus 1 on the bottom, this is the trick to use. One very well-known identity is that the integral from 0 to infinity of x to the k over 1 plus x to the n dx is actually just equal to pi over n cosecant k plus 1 over n times pi. And this is an identity I've covered in many different videos, and I use it all the time. Now, in this case, we have n equals 2. So let's go ahead and just plug that in right now. This is going to be pi over 2. And I can just write this as k plus 1 times pi over 2. Now, of course, in this case, we're going to have k equals 0 since we don't have a power of t in the top. But before we do that, we want to introduce that ln squared. So the way we're going to do that is we're going to differentiate with respect to k. So we differentiate both sides with respect to k. We're going to get the integral from 0 to infinity of x to the k over 1 plus x squared dx equals pi squared over 4. Sorry, negative. I forgot the ln too. And then we're going to have, I guess, cosecant and then cot also of pi over 2 k plus 1. Excuse my very bad notation here, but that just means cosecant of this times cot of this, right? And then we're going to go ahead and just plug in differentiate again. And we can also go ahead and just plug in everywhere we see k with 0 in this situation, since we don't have a power on the top. We're going to end up with negative, or I guess positive now, with pi cubed over 8 times cosecant cot squared of pi over 2 k plus 1. But in this case, again, when we plug in k equals 0, we're just going to get pi over 2, and cot squared of pi over 2 is 0. So that's just going to go to 0. And our other term is going to be the same thing we saw before, cosecant cubed pi over 2 k plus 1. Yeah.
Let me see if I can take Shadow for a quick 15-minute walk.
Okay.
And I'll be ready to go.
What time is it?
I think it's 6.
Okay.
Do you want to eat? Or
No.
eat later?
Later.
Okay, if you need a snack, there's muffins, there's
Yeah.
lots to sell, and I'll be back.
Can't figure out where this extra 2 came from. And if we go ahead, this is just going to go straight to 1. I'm sorry, I just noticed a mistake I made earlier. The integral from 0 to 1 of t to the a ln squared of t dt is actually equal to 2 over 1 plus a cubed. So this is actually equal to 4i, not 2i. So sorry about that. And so this is going to be our 4i. Of course, this is just ln squared of x, right? And so overall I is just going to equal pi cubed over 32. All right, let's go ahead and look at our last method. So this is going to be using a pretty cool theorem, which says that the sum from negative infinity to infinity of f of n times negative 1 to the n equals the sum of the residues of f of n, or f of z times pi cosecant of pi z. And this is a little bit odd, of course. I'm not going to go through the whole proof right now, but essentially the way this is done is we construct a big contour in the contour integral that goes out to infinity. And every point on the inside, at every integer, is going to be pi cosecant pi z is going to have a pole, and the residue is going to be equal to negative 1 to the n, if n is that pole, right? And so that means when we multiply by f of z, as long as f of z doesn't also have a pole at that point, which in this case our f of z doesn't have a pole at any integer, so we don't need to worry about that. This only works for functions that don't have poles at integers, right? So at every point, it's just going to spit out the value of that function. And then at all residues of f of z, that's also going to contribute to this integral, and then we have to do a little bit of work to prove that the integral goes to 0. And so essentially, both of these add up to the integral, which is 0, so they're negative each other, right? So let's go ahead and evaluate these residues. There's a more detailed proof. I'll show a paper which describes a more detailed proof in the description, but I'm not really qualified to go through that whole proof. I'm just going to use the formula. So in this case, our f of z equals 1 over 2n plus 1 cubed. And so that means our pole is going to occur at, or not 2n plus 1, 2z plus 1 cubed. Our pole is going to be at negative 1/2, right? So let's go ahead and evaluate that. So we're going to go ahead and use the derivative trick. So we're going to be taking the second derivative of pi cosecant pi z over 2z plus 1 cubed times z plus 1/2 cubed, then taking the limit as z goes to negative 1/2. So that's a little bit crazy right here, but essentially these two are just going to cancel, and it's just going to be an 8 on the bottom. And just like with the other two methods, the entirety of this answer is just going to come from the second derivative of pi cosecant pi z. So that's every single method I've done here all leads to the same relation to the cosecant function, the second derivative of the cosecant function, I should say. And that's generally the case when you're doing a math problem like this, because generally the character of the sum that you're solving or the integral that you're solving is going to be related to a certain way that you can solve it. And though you can solve it in many different ways, they're all going to lead down the same pathway. So you guys can go ahead and evaluate this limit right here, and you're going to see, or of course we're going to actually take a negative of that because of this negative sign right there. So you can go ahead and do that limit, but it's pretty much the same thing that we've been doing this whole time, and you will get the same answer that we've gotten, which is pi cubed. Or actually, you'll get something different since we're getting the sum from negative infinity to infinity, right? But we're looking for the sum from 0 to infinity. But if you just go ahead and reorganize the terms, you can go ahead and solve for our sum. And it shouldn't be too difficult. I'll leave that up to you guys, but you will get that our sum is equal to pi cubed for 32, as we have in all our other methods. So I hope you guys enjoyed this video. We did a lot of really cool methods to solve this awesome summation. I'm going to say that the integral, converting to an integral method is definitely the best way to go for most situations, since it's a really helpful tool when evaluating infinite sums. Definitely should not go underappreciated, and it works for a lot of different sums. Using my special function is something that you don't necessarily need to learn, since it's not going to pop up in many situations, but I just wanted to throw in stuff from a previous video that you guys might recognize. And this last method is also definitely a cool trick that you're going to want to get in your toolkit because it's going to come up all the time. It's going to be definitely really good for evaluating sums. So anyway, I hope you guys enjoyed the video. I hope you had a good time and enjoyed the methods I showed. If you want to see more content like this, just let me know. If you want to see it go in a different direction, please, I'd love feedback in the comments. And yeah, I hope you enjoyed the video, and I'll see you next time.